Welcome to our YouTube channel. So today we are going to be solving question on section classification. So this is the example we are going to be treating for today. Determine the section classification of 610 by 229 by 125 universal beam of grade S275 subjected to bending. So this is the section of the beam. As you can see, this is the depth of the section. This is the width of the section. This is the thickness of our web, and this is the thickness of our flange. So the first thing to do anytime you see a question like this is for you to list out the section properties of the section. So that's what we are going to do now. And the section properties, we are going to be getting the section property from the steel table. So from our steel table, you are going to trace this section of beam 610 by 229 by 125 under the universal beam section. So that's what we are going to be doing right now. From the steel table, we are going to write out the depth of the section, the breadth or the width of the section. We are going to write out the thickness of the flange, the thickness of the web. We are going to write out the ratio of local buckling for the web, which is D all over T. And we are going to write out the ratio of local buckling for the flange, which is B all over capital T. So from the steel table, the depth of the section is 612.2 mm. The width is 229.2 mm. Is 229.0 mm. The thickness of our flange is 19.6 mm. From the steel table also, the thickness of our web is 11.9 mm. So the ratio of local buckling for the web is 46.0, while the ratio for local buckling for our flange is 5.84. And we also write out the sectional area kg, which is equals to 159 centimeter square. So all of this we are going to be using in solving our next step, because we are going to be needing the thickness of flange and thickness of web to determine the design strength for this question. So now the next thing to do is for us to determine or check for buckling. design strength. For the flange, from the section property we listed earlier, the thickness of the flange T is 19.6 mm. So now, you are now going to check on table 9. From table 9, we are going to check to know what our Py, which is the design strength of the flange, is. Now, if the thickness of the flange is less than 16 mm, it's going to be 275. That's what our Py is going to be. And if the thickness of our flange is less than 40 mm, our Py is going to be 265. But because the value T, which is the thickness of our flange, is less than 40 mm, our Py is going to be 265 Newton per millimeter square. So now we will now determine our this using this formula 275 all over Py. So now we already know what our Py is for the flange. You are going to substitute the value of Py, which is 265 Newton per millimeter square, in this formula to get this. So that we will now say this is going to be the square root of 275 divided by 265, which is going to give us 1.02. That is the value for that. So now we are going to do the same for the web too. So for the web, we all know from the section property we listed, the thickness of web T is 11.9 mm. The same thing is applicable here. When the thickness is less than 16 mm, I said earlier that it's going to be our Py, which is the design strength, is going to be 275. This you are going to check it from the table 9 that I wrote here. So it's from the table 9 that you are going to get all this value from. But the thickness of the web now, we already know that is 11.9. So our Py is going to be 275 Newton per millimeter square. So we are going to calculate for this too, using this formula 275 divided by Py. Now we know the Py for the web. The Py for the web now is 275. We are going to substitute for Py in this formula so that we have square root of 275 all over 275. This divided by this is 1. The square root of 1 is still 1. It's 1.0. So that is all for the design strength. So the next thing we are going to do now is the section classification. So for the flange, you will check on table, table 11. So for the flange now, so from the table, we are going to the ratio of local buckling B all over T limit for class 1 plastic rolled section is 9A. So that this will thereby be equal to, because you know the value of this already, so it's going to be equals to multiply by 1.02, which is equals to 9.18. So now, since limiting value (9.18), which we just get from this, is greater than 5.84, which is the actual value, of the ratio of local buckling for the flange, since this which we just calculated now is greater than that one now, we can therefore say that the flange is class 1 plastic. So the flange is class 1 plastic because the calculated limiting value that we have here, the one that we just calculate now, is greater than the actual value of the section. So that's why we now say that the flange is class 1 plastic. So we are going to do the same thing for the web also. Web. Now, remember from the question, it is subjected to bending. So on our table 11, and you also look at the section of the beam, that it is symmetrical. Yes, the beam is symmetrical about the axis of bending. So, therefore, the neutral is at the mid depth, since it's symmetrical about the axis of bending. So, we will now say that the d all over t limits for class 1 plastic the neutral since this section is symmetrical about the axis of bending, that is why we are going to use the neutral isothermic depth, so that our limiting value will be, that is d all over t, will be equals to a t large, so that this will be equals to, we know that the value for the wave that we calculate for this is 1. So it's now going to be 80 multiplied by 1, which will be equals to 80. Now, we will say, since limiting value (80), which is this that we just calculated, is greater than 46, which is the actual value, we can therefore say the wave is class 1 plastic. Therefore, the section is class 1 plastic when subjected to bending. So that's all for this question. Thank you for watching.